Okay, so talk's comprised of 3 parts. First, I'm going to talk about a big sort of choice you have to make at the architectural level. Are you going to use a monolithic architecture or a microservice architecture? Because there's trade-offs there. Then I'm going to talk about how an event-driven approach solves some key challenges that you have to deal with when you're building a microservice architecture. And then I'm going to finish up by talking about how Docker fits in and how it can simplify both deployment and development. So let's get started. So let's imagine that you're building a complex application, which probably almost everyone in this room is, right? We don't spend our time building trivial applications. And the example I like to use is an online store. And I'll show bits of the design in a moment. But I think it's safe to say that in order to successfully develop software, there are 3 things that you have to get right: the architecture, the organizational structure, and the processes that you have to use. There's a strong consensus around the idea of rather than having very, very large development teams, 20, 30, 40, or even more people, really what you want to do is break up your engineering organization into a team of teams. Each team is small, comprised of, say, at most 12 people, ideally just 6 to 8, right? Those teams should be autonomous, able to work fairly independently. And then there's also a lot of consensus to say that we should be developing using agile processes, right? Ideally, using continuous delivery, or better yet, continuous deployment. So that's organization, small, autonomous, agile teams who are delivering continuously. But what about architecture? So at a high level, there's 2 choices that you have to make. Am I going to build a monolithic application or a microservice-based application? So let's look at the monolithic approach. So here's my online store. And as you can see, it's both layered and modular. So there's a presentation layer that's exposing a REST API, but also generating HTML for the browser. There's various modules that implement different pieces of business functionality, like the catalog service, the review module, the orders module, and so on. So it's got a nice layered modular architecture. But when we use the monolithic architectural approach, we package everything up as the application, right? Just this big monolithic application. So in the Java world, that would be an EAR file, a WAR file, or a jar file. And there's analogous to packaging mechanisms in other languages as well. And the application uses the database. So, in fact, most applications I've built over the years have had this architecture. And there's a good reason for that. This architecture, or applications with this architecture, in the beginning, are pretty simple to develop, test, deploy, and scale. All our tooling is around building the application, testing is easy, and so on. The trouble that you have is that successful applications have a habit of growing. We don't just build an application and stop development. We continue to develop the application. So the team of developers is just making the application a little bigger every day, committing code, right? And you do that for long enough, in some cases 10 years. The other day I was talking to a client where they started selling they had a very successful demo, they started selling it, and 10 years later they had an application that was 1.5 million lines of code. And the problem you have is once you have a large, complex application, any notion of being agile just goes away, as everything about developing and deploying that application becomes extremely painful. Also, from an organizational point of view, because everybody's contributing to the same code base, there's really no autonomy between the teams. The process of delivering or releasing an application involves complex merging and days of pain and so on. You end up in this situation that I call monolithic hell. And I'm sure some of you are living that every day because it's quite common. I feel like there's a certain inevitability that given enough time, your key application will become painful to work with. So what's the solution? Well, the solution, of course, is to use the microservice architecture. And what got me interested in this approach before the name was before the name existed, was I read this book, The Art of Scalability, which to me is a must-read book written by some architects who worked at eBay. And in the book, they have this three-dimensional model of scalability, another use of three. And so there's three different axes along which you can scale your application. So there's the x-axis scaling, which is where you run multiple copies of your application behind a load balancer. That's running multiple monoliths. There's z-axis scaling, where you're running multiple copies, but instead of it running behind a simple load balancer, it's behind a router that inspects the request and uses some attribute of it to route that request to a particular server. So in the database world, that would be sharding, where you use the primary key of a row to decide which server that row should reside on. Both x and z-axis scaling are all about monoliths. But what's really interesting is y-axis scaling, or in other words, functional decomposition. So that's where you break up your application, you break up your monolith into a set of smaller applications or services. And that to me is my definition of the microservice architecture, is functional decomposition. So when we apply that to the online store, we end up with an architecture that looks like this. So what were previously modules within our application now become standalone, independently deployable and scalable services, each one of which has its own database. That's a key attribute of the microservice architecture, which has a lot of benefits, but creates problems that I'm going to talk about in a little while. And then sitting in front of those services is the API gateway, which acts as a facade. It exposes an API that clients of those services use, clients such as a web application, or a JavaScript client running in a browser, or a mobile client accessed via a REST API. So that's the microservices architecture in a nutshell. And the nice thing about it is that it enables agile development and continuous deployment. It also enables the teams to act autonomously. So each team owns one or more services. They're able to develop that service independently, deploy it independently, and scale it independently. So it sort of fits very well with sort of modern organizational thinking, and also modern thinking around processes as well. So it's really good. And there's other benefits as well. It lets you much more easily adopt new technologies, because when you're writing a new microservice, you can pick a new technology at that point. You're no longer stuck with using the same technology stack throughout your application, which will become increasingly obsolete over time. So there are some drawbacks, however, right? And by far the biggest drawback of the microservice architecture is complexity. Things are sort of complex at this point. So number one, you're developing a distributed system. So what that means is that whereas before, when module A called module B, that was just a language level method call or function call, really, really simple development, you now have to deal with inter-process communication, which on the one hand, yes, there are frameworks for doing messaging and frameworks for doing RPC, but it's just complicated, more complicated, right? Not only that, you have to deal with this concept of partial failure, which you did not have to deal with before. So in other words, when you call some other service, that service might not be up, or it might be really, really slow. So you might not get back a response ever. It might just sort of permanently hang. And you as a developer have to be mindful of that and have to program for that scenario. Also, as I mentioned, we've split up our databases, and yet we still have business transactions that need to maintain data consistency across those databases. And that becomes really tricky, especially because we can't use the traditional approach of two-phase commit. Distributed transactions are not a viable option for modern architectures. Also, testing is more complicated as well. because you might want to test a service, but that service could have a whole tree of transitive dependencies. Also, just deploying and operating your application is a lot more complex. Whereas before, there was one monolith, and you just ran n copies of it. Now, there are tens or hundreds of microservices, and you need to have so many instances of each one of them. So there's many more moving parts that have to be deployed and monitored and managed and so on. Nice thing is that, like as we saw in the keynote today, there's sort of Docker-based orchestration technologies that can actually make that what can take away an awful lot of the pain. It's also challenging to implement features that span multiple services. A whole bunch of planning has to be done. So that's just another complication. But the nice thing is, as I hinted at, right, like there are solutions to most of these problems. Either sort of process, like you can do scaling, you can use scaled agile techniques to coordinate across the teams. Docker orchestration technologies take care of a lot of the deployment pain. And later on, I'm going to talk about how you can use events to ensure data consistency across different databases. So it's better. And unlike with a monolithic application where there are no solutions to its complexity and you just have to suffer quietly, we've got viable solutions here. So in general, for large, complex applications, the benefits of microservices tend to outweigh the drawbacks. So that's good. But having said that, there are a whole bunch of issues to address, like how do you deploy them? How do they communicate? How do clients of the application communicate with the services? How do you actually break up your application? And how do you deal with these distributed data management problems that result from breaking up your databases? So there's just sort of a whole bunch of issues. And I'm going to touch on a couple of them, namely using events to manage data consistency and using Docker to actually deploy your system. OK, so that's look at the whole event-driven approach. So if we think about question, what's the database architecture in a microservice system? You've got two choices. You could have a single shared database, or you could have a database per service. And I've kind of already hinted at the fact that you actually have a database per service, but let's look at the concept of a shared database. So in this e-commerce application, you've got the order service that has the order table, and you have the customer service that has the customer table. And so the order table's got columns like the order total. The customer table has columns like the customer's credit limit. So each service owns some tables, but they also access one another's. So for instance, in order to check that the customer's credit limit will not be exceeded by a new order, the order service goes and looks at the customer table. Likewise, the customer service, in order to calculate the available credit for a customer, goes and looks at the order table. And on the one hand, that's kind of nice. This is actually a kind of simple programming model, right? We're used to programming with ACID transactions that enable us to easily enforce invariants like credit limits and so on. So it's kind of nice. And also operationally, it's good. There's just the database to manage. So the DBAs and the ops people are happy. But on the other hand, there's tight coupling. So for instance, if I'm working on the order service and I want to change the database schema, I have to go and talk to all of the teams whose services are also accessing the order table. And as you know, once you kind of have to coordinate with other people, other teams inside your organization, things slow down. So the teams lose their autonomy. And what's worse, in some organizations, this is common today, people lose track of who's accessing what table. And as a result, you can't change anything, right? So it's sort of like, it's a slippery slope and best avoided. So the recommended approach in a microservice architecture is for each service to have its own database. Or another way of putting it, each service should have its own private data that is only accessible through that service's API. You want to properly encapsulate the data. So the order service has an order database that has the order table. Customer service has the customer database that has the customer table, and so on. And this ensures that you have loose coupling, which is good. On the other hand, it's a bit more complicated. You might actually have to be operating multiple databases, especially if you've adopted a polyglot persistence architecture and you're using a variety of NoSQL and SQL databases as well. So your ops people have a more complex infrastructure to manage. Plus, you have this problem of, well, if I've split things up, how do I maintain data consistency across multiple databases? Especially because in modern applications, you cannot use two-phase commit. Because of things like the CAP theorem, plus just the practicalities of using distributed transactions, it tends to be a very bad choice for modern applications. So this creates problems. So, to use the example I've kind of hinted at earlier, so in this application, let's suppose that customers have a credit limit. And so when you want to place an order, you have to verify that that order will not exceed the credit limit. If orders and customers are in the same database, trivial. You just begin a transaction, access the data, create an order, commit it, and you're done. And the ACID transaction model handles the scenario where multiple requests are simultaneously trying to create orders. You get the serializable aspect of database transactions. But if you split up orders into one database, customers in another, how on earth, and you're not using two-phase commit, how on earth do you do this? So the solution, of course, is to use an event-driven architecture. And the idea is that whenever something happens of significance, such as a state change, or in other words, when one service updates data, it publishes an event. Another service can consume that event and react accordingly, update its own data. And by basically chaining together a series of transactions where one transaction emits an event that triggers another transaction, you can achieve eventual consistency in your system. So in the order management system, when a request comes in to place an order, the order service creates an order in a pending state. It emits an event to indicate that it's done that. That event is consumed by the customer service, which goes and performs the credit check and actually reserves credit. It keeps track of the fact that order XYZ has allocated so much of the available credit. And then it emits an event indicating the outcome of the credit check. So if the credit reservation was successful, it would emit a credit reserved event. And if it was unsuccessful, it emits a credit check failed event. Those events get consumed by the order service, which can then change the state of the order accordingly. So instead of this happening in one local ACID transaction, what we have is a series of, 3 local ACID transactions, and eventually the state becomes consistent at that point. So that's an approach that I first read about eBay using to maintain consistency across their partitioned SQL databases some number of years ago. But there's a little challenge. In order for this to work reliably, you actually have to atomically update the database, like insert an order or change the state of the order or a customer, and emit an event. So there's 2 things that have to be done atomically. And if you think about it, the traditional way of doing that in an enterprise application is with a distributed transaction, right? You begin a distributed transaction, you update the database, you update the message broker, and then you commit the transaction, and that will guarantee that those 2 things happen atomically. But of course, as I've discussed, you cannot use distributed transactions in modern applications. So you're sort of like, well, how am I going to reliably publish events? It turns out there's a whole variety of strategies that you can use, ranging from the application using the database table as a message queue. So that's the bottom one. You can actually do it with database triggers. You can tail the database transaction log. And then there's also a technique called event sourcing that I've been using successfully for a while now. And I'm going to talk about, there's actually an article that I wrote that goes into this in more detail. I'm just going to focus on event sourcing, which is really, really interesting. And the whole idea with event sourcing is it's basically an event-centric approach to persistence. And of course, in other words, so for instance, with the way you'd actually store an order is as a sequence of state-changing events. So when you create an order, you insert an event into an event table saying that the order was created. You would then, when, say, the order was approved, like the credit check was succeeded, and you'd insert an order approved event. And then when the order was shipped, you'd insert an order shipped event. And that's the official sort of system of record for that order. So you don't have a row in an order table that's got the current state. All you're storing is a sequence of events. And the reason that helps in this scenario is rather than you having to update the database and publish an event, you simply insert an event into the event table, which is one atomic action. So it solves the atomicity problem. And then if anyone is, at least conceptually, if anyone is interested in subscribing to the events, they can just pull the event table. In practice, you'd use a much more elaborate scheme than that, but that's sort of the big idea. And then, if you need to reconstruct the current state of the order, you load its events, and you can think of this process of replaying them to reconstruct the current state. In a functional sense, you're actually doing a fold over the stream of events to recompute the current state. So that's event sourcing. It's an event-centric approach to persisting your domain objects that at the same time has this wonderful benefit of you're generating a stream of events out of your system, which, among other things, solves the data consistency problems in a microservice architecture, and also in scenarios where you're using NoSQL databases as well with limited transactional capabilities. It also means that you've got this wonderfully reliable event publishing mechanism. So when anything happens within your system, an event is published, you can feed that into a predictive analytics engine. You can use it to send out user notifications via email or via SMS. So it's like whenever something happens, an event is generated, which can be then consumed somewhere else and get something done. It also eliminates the object relational impedance mismatch problem. Because you're no longer storing domain objects, we no longer have the problem of mapping them to a relational database schema, because all we're storing are the events that have a simpler structure. Also, because each state change is represented by an event, we have a 100% reliable audit log. We can save the identity of the user that caused the change in the event. And if there was no change, no event, we're just sort of guaranteed that we've got this reliable audit log, which is really, really good, as opposed to having to bolt on auditing as an afterthought. Also, because we're saving the entire history of each domain object in this system, we can actually go back in time and ask what the state of an object was historically. So we can perform temporal queries, which is extremely powerful. there's some domains that are heavily regulated, so you need to know who did what when, or what was the state of the world when a particular trade happened. And so this system actually preserves that. And then not only that, we've actually, from a sort of system point of view, we have a complete history of everything that has happened in the system, at least conceptually, since the beginning of time. So when today we implement a new feature, we can actually feed past events, all of the past events, into that the module that implements that new feature, and it effectively behaves as if we had implemented that feature from day one, which sounds really cool. Sounds cool. I haven't actually tried it, but you can imagine doing that, right? But of course, like everything, there are drawbacks, right? So it requires an application rewrite. It's a different way of structuring our core business logic. Though the nice thing is, if you're migrating to a microservice architecture, you're having to do a code rewrite anyway, so it could kind of fit in with that effort. It's also a somewhat slightly weird and unfamiliar way of structuring your business logic. So there's a learning curve. The nice thing is that event sourcing has sort of been around for quite some time, and there's this, it's a subset of the domain-driven design community. And so there is this body of knowledge and articles and resources that can help get you started. Another interesting challenge, at least in theory, is that these events, once they've been published, never go away. And that's great because you've got this durable audit trail for your system. The downside, of course, is if you have a badly designed event, you might have to live with it forever. If ever you do a replay of all the past events, you have to deal with some badly designed event. Though usually events have a pretty simple structure. They're very much rooted in the problem domain, so they tend not to be very complex. But there are issues around event schema evolution. Also, you have to handle duplicate events. So you've got to have either idempotent event handlers, or you have to do duplicate detection. But there are usually very simple strategies for doing that. Also, querying the event store can be challenging, right? Like if you want to, imagine you're storing account debits and credit events, and you want to write a query that finds all accounts that have a particular balance. Your SQL query would actually have to kind of combine the events. You'd end up having to write nested SQL queries, which would be kind of complex and possibly inefficient. So there's a challenge there. So there's some, like everything, there are definite trade-offs. But my sense is, event sourcing has been around for a while, and to me it was always a curiosity, but as soon as I started building microservices, it became a great way of solving the data consistency problems. And what's nice is that there is a strategy for dealing with queries. So let's imagine that you want to find in your system, recent valuable customers. So customers who have recently placed high-value orders. Now, if everything was in the one database, that would be a trivial SQL query, right? Just a join between customers and orders with the appropriate where clause. Now, in a microservice architecture, that's no longer easy. Customers and orders could be in different databases, so we can't do that. And then what's more, if we're using event sourcing, writing a query involving the current state is no longer trivial, as I mentioned earlier. So this is a problem. The nice thing is there's an architectural approach known as command query responsibility segregation, where you split your system in two. You have the command side that's implementing, that has the domain objects, and it handles the commands, the HTTP puts, posts, and deletes. You have a query side that handles the HTTP gets, by querying one or more materialized views of your data, which could be Mongo, could be Redis, could be Neo4j, could even be SQL or Elasticsearch, depending on the types of queries that you need to execute in order to perform those GET requests. And then what's really cool is that the two sides are kept synchronized. The views are kept synchronized by consuming the events that are coming out of the command side. And so this is a way of basically supporting a diverse range of queries in a high-performance, scalable way, while at the same time using event sourcing. So if any of you are using, say, Elasticsearch in conjunction with MySQL, in a sense, this approach is sort of a generalization of that concept. You know, there's definitely complexities there, but there are also some pretty big benefits. All right, so kind of talked about some architectural ideas, right? You know, microservices at a high level, using events and using CQRS to deal with data management problems. And I want to finish up, you know, since this is DockerCon, I have to talk about Docker, right? But what's cool is, you know, I've actually been using Docker for, I don't know, a couple of years now. Just blows, and actually this is the first time I've been to DockerCon, and I guess this Docker thing is catching on, right? Just blown away by the size and the energy of this event. So, okay, so, you know, so you've decided, you've built your system using the microservice architecture, and it's like, well, how do we deploy it? And we have, you know, you now have some really unique challenges, right? Instead of a single monolith, albeit a large one, you've now got lots and lots of services. So there's a lot of moving parts that need to be deployed, orchestrated, and monitored, and so on. And there's a lot of sort of interesting issues that you have to deal with. So services can be written in a variety of different languages and frameworks, and maybe even versions of languages and versions of frameworks, so that there's a deployment challenge there. Each service consists of multiple instances for scalability and availability reasons. Building and deploying a service should be fast, right? We want to practice continuous deployment, so it shouldn't take a long time to build a service and have it up and running in production. We want to be able to deploy and scale each service independently. The services should be isolated from one another, so we don't want a malfunctioning service to consume all of the CPU or all of the memory of a particular machine. And then also the process of doing deployment needs to be reliable. We shouldn't stress about it, right? We should be able to do it many times a day without having a panic attack or having late nights or anything like that, you know, which is sort of the traditional deployment scenario. And not only that, it should also be cost effective, right? Because, well, most of us work for businesses that have to generate profit, right? So you know, having cost-effective production environments is important. So it turns out, of course, there's a variety of different deployment options, right? So ranging from the traditional approach of, well, just getting a few machines, giving them cute names, and running multiple instances of services on each one, right? So I'm calling that the multiple services per host pattern. So that's kind of the old school way of doing it, and probably, you know, it's generally not a good idea today. And so the better approach is to have a single service instance on each host, and a host is either a virtual machine, like an EC2 instance, or it's a container, as in a Docker container. And once you get into it, you know, there are various trade-offs involved with each approach. But, you know, I think sort of the whole container-based approach is by, you know, starting to prove itself as, you know, an incredibly effective way of deploying your applications. So, and of course, you know, Docker is the way to do it. This, by the way, this was a container ship, Benjamin Franklin, that visited the port of Oakland at the end of last year. It's like 1,400 feet long, and it has 18,000 containers on it. So, you know, got to have the obligatory container ship photo in the talk. So of course, the big idea, right, is that you take your service, compile it if you need to, and then you package it up as a container image, and then at runtime, each instance of your service is a container that is probably running on a virtual machine. Or it could be running on bare metal. That's sort of emerging to be a viable option as well. And that's really good, right? Containers give you good isolation between your services. They give you good manageability, right? Also, it encapsulates the implementation technology. Once you've packaged up your application as a container image, it doesn't matter that it's a Ruby or a Node or a Java or Scala application. It just becomes a container image that can be started and stopped. Also, the container mechanism is a super lightweight OS-level virtualization technique. So you get, unlike virtual machines, you get very, very efficient resource utilization. You can pack multiple containers on a virtual machine. Also, it's incredibly fast as well. So like on my laptop, it takes a few seconds to build an image, a little long, say 20 seconds to push it into a registry, 20 seconds to pull it down onto a production server, and then when you start a container, it just starts up immediately. So what's that? 45 seconds from the build finishing to a container in the production environment, which is really, really cool. So that's really good. And then not only that, I have found Docker to be invaluable during development as well, specifically with what Docker Compose gives you, right? And this came up in the keynote, where getting a developer desktop set up with the right versions of all of the infrastructure services that you need has historically been a pain, right? Because especially in modern applications where we're going to have a whole host of services, now that just gets represented by a Docker Compose file, and this one says, well, I need RabbitMQ 353 and MongoDB 3.0.4, and then I just go Docker Compose up, and there's my sort of infrastructure services running, which is incredibly useful. Not only that, when it's time to do sort of some notion of end-to-end test or integration test between the services, it's really, really convenient to just have a Docker Compose file that deploys those services. So I just go Docker Compose up, and it just launches instances of all of my services. And so that's a regular part of my sort of day as a developer is making use of Docker Compose for that. And it's pretty basic stuff, but it's made my life as a developer a lot easier. And then not only that, so for every service, I have a Jenkins-based deployment pipeline that basically emits a Docker image. And what's one of the interesting things one of the intermediate steps is after actually building the Docker image, it uses the Docker daemons REST API to actually launch a container, and it just runs a smoke test on it. And that's kind of nice, just to have a sanity check that I haven't built a Docker container that's completely broken. And then, then the other thing that's sort of one final point is that Jenkins itself is actually deployed as a Docker container along with Artifactory, that's sort of a Java repository server, as Docker containers on an EC2 instance. And then any data that I want to persist is actually on an EBS volume, and then volume mapped into the container. And so I've had, been running this kind of setup for probably a year and a half now, if not longer. And it's been really, really good. So Docker, microservices just works really, really well together. And so that's my talk. Hope that you found it useful. So it's kind of in summary, right? Like, you use microservices to accelerate development. You want to use an event-driven architecture to maintain data consistency across your microservices. And you want to use Docker to simplify not only the development of your applications, but also the deployment. So that's my talk. Hope you found it useful. And please, if you've got questions, contact me, email, Twitter, and also check out learnmicroservices.io. So thank you.